nanomechanical systems. And our scientific host today is Professor Sergei Flach.
Okay, so welcome everyone. It's a great pleasure to have Ron Lifshitz, Professor Ron Lifshitz with us. I think we first time met ages ago in the 90s, I think, somewhere in Tel Aviv University in the physics department. So let me tell you a few words about Ron. Ron did his undergrad studies at the Hebrew University in Jerusalem, and then he moved for his PhD from 1995 to Cornell University, and his advisor was no one less but David Mermin. I think that's the Mermin-Ashcroft author, and the Mermin-Wagner also. Is it okay? So very good. So everyone knows Mermin, of course. Good. So then he moved. He stayed at Caltech as a research fellow, and then he moved to Tel Aviv University as a senior lecturer in '99. He rose through the ranks, became associate professor, and since 2013, he's full professor at Tel Aviv University. He also took administrative duties. He was for 4 years the chair of the Department of Condensed Matter Physics. And since 22, he's the vice dean for teaching faculty of exact sciences, Tel Aviv University. And he has lots of publications. He's an expert in quasicrystals, which is, I think, what he will not talk here about. But, you know, for those of you who are interested, this guy knows a lot about quasicrystals. He has lots of publications, over 70 publications and lots of citations. Just check him out on Google Scholar. Maybe I should mention a few awards. He has received among many other, was the Jean-Marie Dubois. I'm not sure whether I'm pronouncing correctly. Award in quasicrystals. What? Dubois, okay. And then he's also the recipient of the Israel Science Foundation Olshwang Prize in Physics and the Caltech Prize Fellowship in Theoretical Physics, and there are more. I don't want to steal your and his time, and we are looking forward to talk on classical and quantum non-equilibrium dynamics of nonlinear nanomechanical systems. Okay, please, let's welcome the speaker.
Thank you very much, Sergei, for hosting me here. Had a nice few hours this morning and afternoon. This talk is an overview of quite a few years of work on very small mechanical devices, where the primary interest comes from the fact that they behave nonlinearly, mechanically nonlinearly. The full talk lasts about 3 hours, so I will skip things during the talk.
That's not what I meant when I said you.
I know exactly. So, but I will need some guidance from your faces to see what to skip and what not to skip. So, I mean, there are various options that we could go through. The full plan of the talk, which, as I said, I will not cover all of these topics, but you can glimpse on them, and later, if you prefer some over the others, we can go to those. I will give a basic introduction regarding why we want to study nonlinear dynamics using nanomechanical systems. Then I will mostly focus on what happens when you have many coupled mechanical devices, so arrays of nanomechanical resonators. And then, again, as a function of time and preference, we can either talk about some neat applications that we came up with. I'm a theorist, so applications aren't real applications, but kind of actual ideas where you can use nonlinear mechanics to do something for you. And then maybe talk about the quantum regime, which has become a major focus in nanomechanical systems in the last 10 or 15 years. But I will start with this introduction, trying to address some basic background that I will then use for the remaining part of the talk. So the first question really is, why do we want to study? Is that thing, press that okay. Why do we want to study nonlinearity using nanomechanical resonators? So first of all, just from the theoretical point of view, these are interesting systems because they're driven and non-dissipative, and they're primarily in some sort of a non-equilibrium state. I was here. As I said, they're nonlinear. it's very interesting and practical to couple many devices together so you can study collective.
Oleg,
Oh, it's not coming off.
call me no.
Okay, don't worry. So we can couple many of them together and study collective dynamics. In many cases, there is noise in these real mechanical systems. And sometimes as a theorist, you want to avoid the noise or at least approximately think that it's not there. But sometimes you actually want to use the noise for doing something for you. And as I said, in the last 10 or 15 years, they've become quantum as well. Now, what our initial goals were when we started working in these systems is to apply the knowledge that we might have from other nonlinear dynamical systems, from questions of pattern formation and so on, and apply them to realistic lab situations. And then basically study interesting questions that have been around for a while, but for a particular set of parameters that are accessible in these particular experiments. And I'll try to stress some of that as we go along. So where is the nonlinearity coming from in these systems? Well, as we know, most things that we see in life, most things that we see in physics.
Okay.
Don't worry about it.
No, we have to stop for a sec.
Okay.
I don't know what to stop, but. Okay. Good.
I'm going to start a movement to banish the use of Zoom when giving seminars.
Oh. But then you are not so
Not that many people, and
Yeah,
Ola, I can see Ola whenever I want. Okay, can I continue now? Does it work? Okay, so let me. Of course not, but my mouse is now not there. Okay. I think I can go on. Okay, so life is not linear, you know. Things are linear approximately. Most things are not linear. Yeah, question already.
Before you continue,
Yeah.
can I ask a quick question? So you just mentioned that now they are becoming quantum. So do we expect to see something abruptly new in the quantum regime?
So
Or what is the advantage of going quantum, let's say?
So let's maybe postpone that later, but the basic answer to your question is that these are man-made mechanical devices. And now in the last 10 or 15 years, we've entered a regime where these human-made devices can be made to work and operate in the quantum mechanical regime. And that's interesting. I mean, can you take two resonators that you fabricated in your lab and entangle them in a quantum mechanical way, and maybe you can use that for something, or just study quantum mechanics on large macroscopic devices or mesoscopic devices and see interesting phenomena. But if I have time at the end, I'll maybe concentrate on some of those. So, but really, where is the nonlinearity coming from? Basically, what I'm saying is that's not the question to ask, because most things in life are nonlinear. But here, any kind of an external potential that you could put on a mechanical device might turn it into a nonlinear one. Here I have an example of a mechanical beam. So this whole beam can vibrate sideways. And so that maybe approximately looks like a harmonic oscillator, a linear oscillator. But once you put a gate or a potential, something that will pull it from the side, then you basically turn it into something nonlinear. So it's very easy to generate potentials that are nonlinear. Often you have geometric effects. So here's a caricature of again, one of these elastic beams that's vibrating sideways transversely. And when it vibrates, it stretches. And when it stretches, the tension changes. And so the spring constant changes. So you have an oscillator where the K of the oscillator changes as it moves, that immediately turns it into a nonlinear oscillator. Now, if you have nonlinearities in the forces that are applied to these resonators, you should also consider the fact that you might have nonlinearities in the damping mechanisms of these resonators. So, we're all used to having a simple linear damping term in our mechanical resonators, something that is proportional to the velocity of the resonator. But then in these systems, you have corrections to that. And typical corrections are in orange here, what we call the van der Pol damping effect, which is something that was discovered by a guy called van der Pol about 100 years ago, where you have damping that increases as the amplitude of the motion becomes larger and larger, like x squared times x dot. But in fact, Lord Rayleigh described something quite similar to that. But in his equation, he had a term that was proportional to the cube of the velocity of the resonator. So these are two typical types of nonlinear damping effects that can come into the system. And there are various other mechanisms that might introduce nonlinearities into these devices. So you should basically assume that devices are nonlinear if you can really not approximate them as something that's almost linear. Now, again, as part of the introduction, I want to describe, I don't know what the background of most people here is, so I don't know how familiar you are with these, but the two prototypical dynamical behaviors of mechanical oscillators, of nonlinear mechanical oscillators. So this is a so-called Duffing resonator. What we have here, in addition to what we teach in our first or second year mechanics classes, is a force that's proportional to the cube of the displacement of the resonator. Other than that, we have the normal linear damping term, and we have the normal external driving force at some frequency omega. And what we see in the response of this system, and I won't give you the exact solution here, but just the plot of the solution, is that for small amplitudes of drive, so if G is fairly small, then what you see are the plots down here. You basically do not see the nonlinearity. You work at very small amplitudes, and so essentially you see something that's very much similar to the Lorentzian curve that you know from the normal harmonic oscillator. But as you increase the drive, as you increase the amplitude of the drive, what you observe are this pulling of the response frequency towards one of the sides, okay? And the direction that it pulls, either to the right or to the left, depends on the sign of the cubic term in the equation here. And I want to point out three important features of the response. So as I said, first of all, you have this frequency pulling, meaning that as I increase the drive, I can pull the amplitude increases as a function of the deviation away from the resonance, from the linear resonance frequency. So here everything is plotted where the resonance frequency is down here at the center, and this capital omega represents the deviation away from the linear frequency. And for a given amount of drive, for a certain color here in one of these plots, as I go further away in frequency, the amplitude increases along with that. So this is this frequency pulling with the amplitude. Another important point is that in the region between these dashed lines here on the left and on the right, I basically have three different solutions for the amplitude of the response. So I didn't say, but A is the amplitude of the response, of course. Three different solutions for the amplitude for a given frequency and amplitude of the drive. Okay, this is basically because we're solving a cubic equation here. A cubic equation can have three real roots. And when we have three real roots, we have three different solutions. And in principle, what always happens here is that the topmost amplitude and the bottommost amplitude are linearly stable. So if I add a little bit of noise to an oscillator that's resonating at this around this amplitude with this amplitude at the given frequency, then the small noise decays away, and this is a stable solution. But the solution here at the center, the middle one here, is an unstable solution. So even if I manage to put my resonator at a state where it's resonating at this frequency with this amplitude, a tiny amount of noise will kick it away from this solution, and it'll go either to the large amplitude or to the small amplitude solution. So these are very typical. And one last thing is that when I do have this, so we call this the region of bistability because I have two stable solutions. And when I do have this bistability, the state that the system will choose might depend on the history of how you operated the system. So for example, if I start at this frequency and I very gradually sweep the frequency, then what I will do is I will trace one solution until it ends, and then I will abruptly drop to the bottom, and then tracing back or lowering the frequency, I will trace the lower solution. And again, when it becomes unstable, I jump up here and go down here. So that's a very dramatic effect here, especially this point here, which is called a saddle node bifurcation. So every point where the set of solution changes is called a bifurcation in nonlinear dynamics. This is a term that will appear as I go along in the talk. So this is a typical sweep from the left to the right of a number of driving amplitudes at sweeping the frequency at different amplitudes on a mechanical, I think this was a micromechanical resonator quite a while ago, 1999.
So from your previous slide, the previous one, what's the meaning of the positive and negative frequency?
So this is relative to the resonance frequency at very low driving amplitudes. So in the equation here, this would be a frequency that I set to be equal to 1 in this equation. Okay, so this would be just the standard linear response frequency of the resonator if there were no cubic term here.
It's also not satisfied because now you're saying that it's a relative, and the frequency is 1 in the negative of 20, relative to 1 is also negative. So what is the meaning of this?
So don't look at the numbers. This is some.
Okay.
Okay.
Sorry. Here you're plotting the Fourier transform of X, yes?
I'm plotting the amplitude of something that oscillates periodically. Yes, if that's what you mean.
So you are, I see. So you are actually solving that equation numerically and then.
Well, this can be solved. I'm skipping that. I'll say a few words about how I solve the next equation for your benefit. Okay. Yeah, but this is quite standard, and I haven't mentioned yet, but there's a very nice review that I wrote some 20 years ago where you can read all the details about how you solve these kinds of equations. These and the more interesting ones that I'll show further on. Sorry, I can't skip here because of the setup. Let me skip this a bit. Okay. The second type of equation that I want to discuss, or nonlinear response that I like to discuss, is the response to what is called parametric excitation. So here, if you look at the equation of motion that I have here, then on the right, I do not have any driving force. Okay, I do not have that oscillatory driving force on the right. But what I do have is modulation of one of the parameters of the resonator. In particular, this is just the spring constant of the resonator. So normally the spring constant would be constant, but here it's being modulated at a frequency that is labeled here as twice the parametric frequency. And this is something that can be implemented in many of the mechanical devices that people can, again, generate and produce in their labs. So this is the type of equation. Again, I have the standard linear damping that I now express using the quality factor of the resonator. I have the linear restoring spring constant, but again, I'm modulating it as a function of time. I have the nonlinear term, the so-called Duffing term that I showed you previously, and now I'm also adding the nonlinear damping term. Okay, so that's the additional aspect that I have here. When we look at this equation, this is a parametric excitation. And what is typical of parametric excitation is that you can see that if I set the displacement to be zero, x equals zero, that's a solution of this equation. So the zero state of the resonator is always a solution of this equation, and the parametric excitation is actually an instability of the x equals zero solution. So again, when I say an instability, I mean that if I add a tiny amount of noise, okay, a tiny deviation away from zero, then when zero is unstable, then the system will flow to a different state where the resonator is oscillating at some finite amplitude. Again, a Fourier transform. I will always talk about the amplitude of something which is oscillating periodically. Below this instability, maybe some of you are familiar with this from optical context. It's the same kind of idea. Below the instability, so if the zero solution is still stable, I already have interesting phenomena that can be observed in these systems. One is called amplification and squeezing. And then, two of them are called amplification and squeezing.
Sorry, then you mean that there is some H critical below which there is no instability.
So I will, yes, exactly. I will show that now. Exactly. And then above the instability, all this nonlinear terms kick in and they saturate the system at some finite resonance amplitude. And I'll talk about that a little bit. And now the question is, how do we solve equations like these? Again, I won't go too much into detail, but what's fairly commonly used is what is called secular perturbation theory or multiple timescale analysis. I'm sorry, I don't know what the background of most people here is, but Sergey can teach you all of this probably better than me.
Oh, they're intelligent enough, they can do it by themselves.
And what you need basically to use these kinds of perturbation theories or multiple timescales analysis is to have different timescales in the system. And in fact, this is a very nice example where you actually see where the different timescales are coming from physically. So I have one timescale, which is basically set by this one here, which is the frequency of oscillation, the linear frequency of oscillations, what was set to zero in the previous plot. I have another time scale, which is set by this damping rate. Okay, the quality factor is basically 1 over this gamma that was written here earlier. This tells me how quickly transients will take to die away. Okay, this is another time scale. And if Q is rather large, say if it's 100 or 1,000, then these transients take quite a while to damp out relative to the frequency of oscillations, to the period of the oscillation. So that's a second time scale. And then in fact, we have a third time scale here because now we have this nonlinear damping term. So this eta parameter here sets a third time scale here. So when we do this secular perturbation theory, it's a very natural thing to use in these kinds of situations from the physical point of view. So again, A here would be the amplitude of the oscillations. So I'm not going through all the derivation or the solution of the equation, but if you run through the secular perturbation theory, then you find or you replace the time dependence of the original equation of motion that we had with a basic algebraic expression for the amplitude of oscillation. So the amplitude and its complex conjugate satisfy this relation now. And one can then use these kinds of equations to study the stability of the solutions. So again, you add a little type of perturbation to the solution, and you see if that perturbation grows exponentially. That would mean that the solution is unstable, or it dies exponentially, and the solution is stable. So the first thing you find out is that the x equals 0 solution is stable up to this so-called stability tongue, because it looks like a tongue. And above this curve here, the 0 solution is unstable. So this is the critical value that you were looking for. So now when I look at the non-zero solution, it needs to satisfy this equation that I have down here. And I can ask, where is this solution stable? And when we look at the stability of the non-trivial solution, the non-zero solution, so again, A is its amplitude, and it's oscillating periodically, then it turns out that it's stable all the way down to this green line. And this green line is a line of these so-called saddle node bifurcations that I showed you earlier, these points where you kind of fall off the cliff and go down to in this case, to a trivial zero state of the system. And again,
sorry.
Yes?
What is the small h over here?
Which one? Here, this was the G in the previous model. That's the amplitude of the drive, of the external drive. Thank you, sorry.
But that was not in the equation, in the parametric.
So in the equation, it was called capital H.
Okay.
And then during the calculation, you need to redefine slightly the term. So it's not exactly that H, but it's proportional to that H in some normalized units. Okay? Yeah, but it's exactly coming from that H. And so what we can do here again is to vary some parameters and see what happens to the solutions. So for example, I can come through here at some particular value of the parametric drive frequency, this omega p, and gradually increase the strength of the drive, increase this amplitude h that you now asked about, okay? So the amplitude of the modulation. What we will see is that we will stick to the zero solution until the point where it is no longer stable. And then we'll gradually see this amplitude A grow from 0 to some finite value, okay? So I scan H, I reach this bifurcation point, and I go up this line, and then if I trace back, I will just trace back the same line. But if I choose a frequency on the right-hand side of this, then what we'll see is that we follow the zero solution all the way up to this red curve here where it becomes unstable. But at the point where this solution became unstable, the other solution has already been stable for a while. Okay, this is this region of bistability. So what we'll see is that as we follow it, where the zero state becomes unstable, we will abruptly jump up to a non-trivial solution already oscillating at some finite amplitude. Okay, this will not be a continuous transition. There will be a discontinuity, and then I will climb up this solution branch. And then when we go down, we will trace the non-trivial solution all the way down to this green line, to this saddle node bifurcation. This is this point over here. And then we will abruptly drop down to the zero state again. Okay, so I see on one side, one kind of behavior. This is in the jargon of nonlinear dynamics, this is called a supercritical bifurcation. It's quite analogous to a continuous phase transition that we know from thermodynamics. And here on the right, we have what is called a subcritical bifurcation. And this looks quite like a first order phase transition in thermodynamics. Yes.
So to analyze the stability, the Jacobian that you are looking at is 2 by 2? Or
maybe we can sit down later and make sure that we use the same terminology.
Yeah, because I'm confused because your A is real or complex?
It's complex.
It's complex.
Yes, yes. Definitely complex. Okay. But not when I write it like this, of course. So here that's the magnitude of A, sorry. So phi would be the phase of the complex A. Okay. And then the final thing I want to say here is that, again, in this parametric instability, we can also see a frequency pulling like we saw in the basic Duffing resonator earlier. If I scan for a given drive amplitude, I now scan the frequency going from left to right and then back from right to left. Then what I will see is that I will be climbing up on, so at this point, the zero state becomes unstable. I go through this whole region where I have a non-trivial solution that is stable. And then at this point over here, when I hit the green curve, I abruptly drop down to the zero solution and I will stay on the zero solution forever. But then when I come back to the left, then I will skip this green point and reach the red point. So I will go all the way here, and only here will I jump up to the non-trivial finite amplitude solution and then trace it back as I go down. So This again is something that can readily be observed in experiment. On the left, you have for a particular resonator here, you have in red the scan of increasing frequency, and then with black, the scan with decreasing frequency. And here you have multiple scans from left to right at different driving amplitudes. Okay, so this really is very well explained by this resonator. So I spent a long time giving you the background, and now I'm ready to tell you what happens when you look at arrays of coupled resonators like that. So this is where things start becoming more interesting.
So to follow that, how fast you can change the frequency?
So I'm a theorist, so I can change it as fast as or as slow as I like.
But when
In the
you change
experiment,
the frequency too fast, then it may not follow.
exactly. That's a wonderful question. And in fact, I was making a joke, but the joke was actually accurate in this case. Because what we had here as theorists was something that one can only dream about, because the parameters were such that the experiment can be done in the regime that is easiest for the theorist to calculate. And the reason for that was specifically because we're talking about nanomechanical resonators. Nanomechanical resonators can oscillate at hundreds of megahertz or even a few gigahertz. Quality factors, which basically tell you how quickly transients die. So how quickly can you make changes to the system and have the system relax back to equilibrium before you make the next change. So if I want a sweep frequency, if I want the system to follow, I need to wait for these transients, okay? So, but even if I have a quality factor of 1,000, which is wonderful, and in a minute I'll say why it's wonderful for the theorist, even if I have a very large quality factor, which means that it takes quite a while, if I'm oscillating at a gigahertz and my quality factor is 1,000, then my transients die after a microsecond, okay? So in terms of experiment, it's very convenient to use. Now, why do I want the quality factors to be high? Because I'm using this separation of time scales, and I really want the damping scale to be much longer than the period of the oscillation, and then I can use perturbation theory, and the whole thing works. So this is a very convenient system, in fact, to exactly do these things, to do these quasi-static sweeps that are slow enough for the system to follow. But still, we do see some transient behavior, and maybe I'll show you some of that even in our theory. Okay, so what I want to do now is concentrate on this parametric excitation. So again, no forces here on the right. And all I'm doing now is that I have a U sub n, so I have the amplitude of the nth resonator, and I'm coupling them just to their nearest neighbors. So linear coupling to the nearest neighbors, the simplest way I can think of making a collective of many of these degrees of freedom. So how are we going to treat this? So very, very briefly, I'll show you a number of approaches that we used in order to treat this kind of an equation. And again, the first thing is to use the same kind of secular perturbation theory or timescale separation.
So basically, the idea is that you change the frequency short compared with the decay time, but long compared with the oscillation.
That's to your previous question, yes. So, but I have enough room to play with that. Yeah, exactly. Yeah. Okay, so how do we treat this kind of equation? So again, secular perturbation theory, the same idea that I showed that was used for the single degree of freedom, to change these differential equations, these time-dependent differential equations, to just algebraic equations for the mode amplitudes, for the complex mode amplitudes. Okay. Here's an example of the algebraic equations, and it's intentionally small because I don't want you to read the details. But what I have here are two coupled equations for A1 and A2. A1 and A2 are just the amplitudes of the symmetric mode A1 and the anti-symmetric mode A2. Okay. But these are, of course, nonlinear equations because the equations originally were linear. And what we want to do is to find the roots for these equations. And then we can know what the solutions are for the system. Again, earlier we had regions where we had a single solution, and then a bistability region when we had three solutions. One of them was unstable and two were stable. Now we have 2 degrees of freedom, so we get a slightly more elaborate bifurcation sequence when we go from one kind of a solution to another kind of a solution.
Where did the time dependence go?
It went along with this secular perturbation theory. So the secular perturbation theory uses the fact that you have different time scales, and it in a perturbative manner, basically turns the differential equations that we started with that are time dependent into algebraic equations for the mode amplitudes. So consider it as a black box at the moment now. Believe me that it works. And later I can show you where you can fill in the details for that.
So these A1 and A2 are complex.
Complex mode amplitudes, yes.
Value, right?
Yes, and so whenever you see a star here, that's the complex conjugate of
Just to get an intuition of this, I mean, simply to convert a time-dependent differential equation into an algebraic equation, what I would do is that I would just do a transformation, like a Fourier transformation.
No, it's simpler than that, but I don't want to get into it here. Basically, what you do is you write your solution as an amplitude times e to the I omega t.
Okay.
But now you allow this amplitude to vary very slowly with time. How slow? As slow as the transients of the system. Okay, so now I put in as a solution to the differential equation as a first step, something that has an amplitude that varies very slowly with time, multiplied by the e to the I omega t. Okay, and then in this case, that's not enough. So you go a second step, and when you try to solve this equation for the amplitude that still is varying slowly with time, you do it again, basically, because I have three time scales here in this system. And eventually at the end, you get something that looks like this.
I see.
Okay, that's the idea of how it works. Sorry.
It's like time-dependent perturbation theory in quantum mechanics, in a sense, like you somehow neglect the time dependence by doing. Okay.
If that helps you understand it. Okay, what I want to show is that once we have 2 degrees of freedom, then this response curve already looks much more complicated, okay? Not very much more complicated, but somewhat more complicated. What I'm showing here is, again, as a function of the frequency, okay, away from the linear response frequency here, so it's the same capital omega as I had earlier. What are plotted here using little dots are the roots of these equations here on the right. But the roots of these equations, basically, what we find here is that there are 4 types of solutions. There's single mode solutions, they're labeled here as S1 and S2, where the system just either goes in the symmetric mode or the anti-symmetric mode. And then there are 2 double mode solutions, this D1 and D2, where it's a particular combination of these 2 solutions. It's 2 single mode solutions. But these are nonlinear equations. It's not that I can take any linear combination of those 2 solutions. It's only 2 very specific combinations of the 2 solutions that can solve these equations. So altogether, we found that there are 4 solutions that are possible. And again, they're plotted using these little dots here that I hope you can see. Now, what's plotted on top of that is a numerical integration of the equations of motion, those that do depend on time, okay? And we're just plotting the amplitude of the solutions that we found numerically as a function of this omega at some strength of the drive, which I did not list here, I'm sorry, okay? But what we're seeing is that as we come from the left, on the left, the zero solution is stable. So we follow it until at this point, the zero solution becomes unstable and this S2 mode becomes stable. This single mode solution that only involves one of the 2 modes, okay? And then I follow that until I hit, at this point here, maybe I should use this for the people at home. At this point, I have a bifurcation. So this single mode solution ends and I drop on top of this double mode solution D1. And then I continue following it, and exactly where we find analytically that it should become unstable, in fact, the numerics also loses its stability from there and drops down to 0. And then from that point on, we follow the 0 solution. As we come back, we actually skip this point completely because the 0 solution is stable all the way down here. But at this point, what we're seeing is a jump up to this. It's not clear to me whether it's the D1 or the D2 state. We follow it a tiny bit, and then it becomes unstable. That's the D2, sorry. It jumps up, and then it actually hits the S1 solution, which we completely missed when we swept the frequency from left to right. So at that point on, we continue following this S1 solution until it loses its stability. We jump again to the S2 and then continue down all the way to the left.
So what happens if you see the jump on S1, now you increase the frequency?
Exactly, and a very important point. So the point was that when we swept from left to right, we completely missed this S1 solution. Now when we swept backward, we ended up on this S1 solution. And in fact, we could change the sweep direction and sweep all the way up and trace it all the way up here. And that was the first message that we had to the experimentalists who were doing these kinds of experiments. And that was after every bifurcation, after every time you jump to a new solution, you want to sweep left and right if you want to trace as much of the solution space that you want to find. Yes.
Isn't it possible here to don't have any fixed points at all in this system? Or you always will have some stable fixed point?
You always have stable fixed points, yeah. It's not that I can give you a proof to that. Maybe so.
What do you mean by fixed point? You mean an attractor, right?
Yeah, so this type of solutions I understand as a fixed point of this equation.
Well,
dynamical
attraction,
equation.
because things evolve somehow in
Yes.
theory.
But something's one way to think about it is that in these equations, setting everything to 0 is always a solution. And if it's not competing with anything else, it will be stable. If it will lose its stability only if it's competing with a more stable solution than it is. I'm running out of time, so I won't be able to show you some examples, but there are examples relevant for that, definitely. Okay, so this is what I just described. This is a particular experiment with 2 degrees of freedom. Doesn't look exactly like this. But features are quite similar when you look at this setup here on the left. So this is one thing. Of course, if I have more than 2 degrees of freedom, solving these coupled algebraic equations also becomes quite cumbersome, and you don't learn a lot from it, I have to admit. So we went to 3 and we solved 3 just to show that we could. But then we realized that that's not going to get us anywhere. Of course, you can numerically integrate the equations of motion, and we did that here. In fact, this is because the experiment that inspired us to start all these calculations had, I don't remember, I think it was 67 coupled resonators. So we didn't want to solve 67 coupled algebraic equations. So we solved the original differential equations numerically. And again, out of lack of time, I don't want to describe the whole set of solutions that we got. But again, the main issue is that we have a lot of these bifurcation points as we sweep frequency to the right and back to the left. And again, after every jump, you want to sweep back and forth to trace as much of the solution space as you could. But again, qualitatively, what we saw here in the numerical calculations could explain what they saw in the experiment. And so that encouraged us to consider this more seriously. I should say that for the numerics, the fact that we have these separation of timescales is actually a burden. Because when you do the numerics, you have to calculate the numerics for the actual oscillations. So the timescale of the numerics really knows about the oscillation period, but all the interesting physics happens at the slower timescale. So you're wasting a lot of computation when you try to follow what these systems are doing. So that's really an inefficient way of looking at these types of systems with separations. of
Can you
time
go
scales.
back, please, again?
Yeah.
Yeah, so in this top right picture, are these cantilever like?
Yeah, so these are, again, what you're seeing here are, again, if I remember correctly, 67 of these
Cantilever.
tiny
And they
elastic
vibrate
beams, and they vibrate sideways,
sideways.
right? And there's the black region here is a hole, so there's nothing
And-
beneath them.
And the interaction between them, this nearest neighbor interaction, this is mediated through what?
So as you see, all the even ones are connected to this contact, and all the odd ones to this contact. And there's an AC voltage that basically charges them.
Yes, but in your equation, you also had a term which was not related to the applied voltage or the AC term, but just, nearest neighbor coupling.
Right.
So
So
what originates?
so these equations are not exactly the same as the equation that I wrote
So what
earlier.
kind of interaction is?
So what happens here is that the interaction between nearest neighbors is the one that is modulated as a function of time. So the parametric excitation in this particular experiment is in the coupling between nearest
But
neighbors.
isn't there also some interaction mediated through the substrate?
There might be, but in
That's
this
weak,
case, in this case, it's much smaller than again, I have a reference list at the end. There's a review that we wrote after we understood these systems a bit better. And then we described the different types of equations that you can write down for these different mechanical systems. So you caught me here. This is not exactly the equation that I was showing.
Can I ask just before?
Yes, of course.
The equations that you are mentioning, the multi-scale equations, usually they are also stiff. So when you selected the method to solve them numerically, can I just ask if you took care of the stiffness? Because usually you have to use implicit methods.
I really do not remember how we did the numerics then. It was quite a while ago.
Yeah.
Maybe we can look at it.
Because the numerics for these systems is usually hard.
So that's what I said. It's hard because you're wasting time on the fast time scale and everything is happening in very slow time scales. That's the main problem.
There is another problem. There's a problem of stability with the numerics.
Right. So, but I don't remember the details of that. So. Okay. So realizing that this is not going to work very well for many degrees of freedom and that this is not very practical for many degrees of freedom, what we did is the thing that we normally do, and that is to perform some sort of a continuum-based analysis and develop what is called an amplitude equation for what the amplitudes of the resonators are doing at the slow time scale. So we should think of the resonators oscillating very, very rapidly, but the amplitudes of these resonators is changing much, much slower in time, and we want to write down an effective field equation for what this amplitude is doing. So I'm going to have a slow time scale and a kind of long length scale describing these systems. So as I said, it's a continuum description. So instead of having an nth degree of freedom describing the nth resonator, I now have a field u of x and t, and only when x is equal to an integer do I actually describe a particular resonator that I have in my array. But other than that, I just have a continuous field. And you go through some algebra, again, a few steps of this secular perturbation theory. And what you find is this partial differential equation now for this amplitude b as a function of a psi, which is a long length scale, and tau, which is a slow time scale. And this describes the slow dynamics of the envelope of this array. And this was kind of surprising. We did not expect an equation to go up to quintic, here a fifth power of the amplitude, but we really need this fifth power to saturate all the lower powers that we have in this equation here. But now we have something that we can work with. So the first, and maybe the only question I'll have time to describe in detail, is the question of pattern selection in such a big array of nonlinear coupled resonators like that. And this is the main tool that we're going to use now, this partial differential equation, this field equation. And the first thing that we can use this equation to do is to draw this so-called stability balloon. So this region in parameter space where we can find stable solutions to our system. We're looking at
The last time you put in for stable, right?
the previous
B to the power 5.
Last time.
sorry.
The power 5 term you put in for stable, right?
So we didn't put it in. It really comes out of the secular perturbation theory. And the secular perturbation theory is just consistent, and it makes sure that if the so I have these linear terms here, and I have these cubic terms here. So 1, 2, 3 cubic terms, and then I have this quintic term. And it's because these cubic terms can have the wrong side and make the system explode. I need this quintic term in order to saturate things, and it just comes. It comes, consistently with the other terms in the perturbation theory.
By you integrate out the fat mode, and then
The what?
you integrate out the fast mode.
Yeah. So again, like I explained earlier, exactly the same idea, but again, you have to do it in 2 steps here because we have three time scales in the system. Okay. So what I'm plotting here is now the strength of the drive. Sorry that I keep changing the notation. It's just from different papers. So this is G now, the strength of the parametric drive on the system. So I'm changing the spring constant of all the resonators simultaneously with the same phase, the same frequency, and the same amplitude. And that amplitude is G. And what I have here is the wave number of just sinusoidal solutions of the oscillation of the amplitude of all these resonators. Okay, so this is a finite array of, and then when we do numerics, it might be 100 or 1,000 or I don't know how many resonators that we're describing now in a continuum description. So it has fixed boundary conditions at the 2 ends, and the different solutions, the kind of normal mode solutions that would be if the system were linear, are characterized by their wave number k. And because this is a finite system, there's a separation, there's a distance between modes, okay, the 2 pi over L, where L is the system size. And so we have different modes, and this diagram describes the stability of different modes. And again, this curve here at the bottom, which is the dashed curve here, which turns red, which then turns, sorry, the dashed curve here that starts here and goes up here is the region up to which the zero solution is stable. Okay, the zero means that nothing is moving in the array. Okay, so that's stable all the way up to this so-called neutral stability curve. So this dashed curve up here. The green line is, again, when I come from a non-trivial solution and go downwards, this is the saddle node line. So this is the line of saddle node bifurcations where a finite amplitude solution abruptly drops to 0 at this point here, okay? In addition to that, I have another curve here, which is this black curve, which is a line which is named a line of Eckhouse instabilities. What happens when you cross that line is that a solution with a particular wave number loses its stability to a solution of a different wave number. Okay, now we have many competing solutions, not only the 0 and the non-zero one, we have many non-zero solutions. And so one of these might lose its stability to one of the others. And this is related to the question that you asked earlier. And that happens through what is called a phase slip. So instead of having n half sine waves in my system, I now have n+1 half sine waves in my system, okay? And when we consider just starting from 0 driving amplitude and gradually increasing the amplitude G, okay, we can ask what kind of solutions are we going to see? And the thing is that what happens is that the first solution that pops out of nothingness is the solution that is closest to a particular wave number, which here is called 0, which is related through the dispersion relation of this array to the frequency that we're driving in. So if the system had a mode exactly at the frequency that I'm driving, that mode would be the one that's immediately excited. But we're driving here at a frequency which doesn't fit exactly one of the modes of the array. Okay, so the first one that gets excited is the one that's closest to it. And that's the one here, which is a little left to this 0. And when we increase the drive amplitude, at some point, we hit this Eckhouse instability. This solution becomes unstable, and we jump to the next solution. Again, we continue increasing the amplitude, it becomes unstable, and we jump here to the next solution, and then again up to this a third solution here to the right. Now we start decreasing the drive amplitude. When we decrease the drive amplitude, we follow the solution. It's still stable until we hit the saddle node bifurcation. At this point, the stability switches and jumps 2 solutions to this solution here. So when we decrease the amplitude, we completely skip the solution that we saw here along the way. And then again, we go down here, and then we jump again, and then we go down to 0. So this is the prediction of what we see here. And what you see on the right is a numerical integration now of the equations of motion, the temporal equations of motion of the system, the differential equations. And we basically recover exactly what we expect to see from this bifurcation analysis that we did here, including the fact that we can actually calculate the B's, the magnitude of the amplitude that's oscillating. So as you can see here, we follow, the blue line is going upwards, so we follow the first solution, we jump to the second one, we jump to the third one, we jump to the fourth one, but then when we decrease the drive amplitude, at this point, we jump all the way down to here, and then we follow down to the left. So this is exactly what we expect to see analytically. So we're doing quasi-static sweeps, and this goes back to the question that you asked earlier. But now we have the ability to focus in, to zoom in time, I mean, and see if we can actually understand how these transitions occur. So from this, for example, from this solution up to this solution, okay, when I hit the end, the point where this first solution becomes unstable. In order to do that, what we can do now, so think that I have 10,000 resonators here, okay, and I'm using a continuum description of them, but now we understand that of all the 10,000 modes that I might have in the system, only 5 or around 5 are relevant to the dynamics at the onset of oscillations. So now I can reduce my number of degrees of freedom from 1,000 or from 10,000 to just 5. And I can focus on these 5. So what I want to do now is expand this solution to this partial differential equation just in these 5 modes. And I've labeled them 0, 1, 2, 3, and the one here to the left, which we don't even see, I call it -1. But it turns out that it's important. I need to include it here. So what I do is I write a solution for the equation, which is just the sum of a small finite number of modes, okay? Small enough that I can follow them numerically. And now if I study the dynamics, so these are the equations. So I get coupled differential equations, coupled algebraic equations now for these mode amplitudes. And this I can now solve. Okay, so for example, when I look at this bifurcation, what I see is that I start with this, so the dashed green line is the B0, the amplitude of the B0 mode. So I start with this solution, and then at tau equals 0, I cross the instability line. I just slightly increase the drive amplitude, okay? What happens is that gradually 2 modes start appearing. These 2 modes are the B1, this one over here, and the B negative one. The blue one down here is the B negative one, which is somewhere over here. These 2 modes start growing exponentially, okay, because they become, they think that they're going to become stable. And at this point around here, this B1 mode has grown sufficiently that the B0 mode loses its stability and it grows all the way up, and this becomes the new steady state of the system, okay? And this B negative one, it was important down here. It started growing, but at this point, when B1 basically won the game and became stable, it also lost its stability. And so all the other amplitudes from this point on are zero until I hit the next instability point. In fact, if you do this calculation and do not include this B negative one that we don't see here, then this bifurcation does not occur. So you really need to include that. So you have to be careful when you use only a small number of degrees of freedom to describe the system, but it gives you a very good description. Let me just describe what happens when we go down, and I think Sergey is becoming, actually I need to finish.
Maybe some quantum.
Yeah, so I'll just show you this, and then I'll say some words about the quantum. I want to describe how this transition occurs. Again, so now we're focusing on the transients to see how the dynamics actually occurs. So I'm starting here where the B3 solution is stable. I hope you can see there's a light blue dashed line here. So I'm starting with the amplitude, a finite amplitude of the B3 solution, and at tau equals 0, I'm crossing this saddle node bifurcation. So at this point, the only thing that's stable is the 0 state here, at this particular dynamical point that I'm sitting. But what happens is that the amplitude of this B3 solution drops very strongly to 0, and for a while, nothing happens. Okay, this is a very small time that we're saying here. A very short time that we're looking at, but nothing happens. And then the first thing that grows at this drive amplitude is in fact the 0 solution, the solution that's closest to the frequency that we're driving in. This is this is what the system would like to respond to if it were stable. And so what we're seeing is that it grows and it reaches its steady state value, but then these other solutions, the B1 and the B negative one, the same ones that we saw earlier, it takes them longer to grow because their exponentially growing rate is not as fast as the green curve. But once they start growing, the green curve loses its stability, and again we see something that resembles what we saw earlier when we looked at the first instability. So this transition, this bifurcation goes in 2 steps. First, we kill the first mode, and then the 2 other modes are building, and one of them survives and takes over. Okay, we can do some very nice additional things and play nice games, but I will skip that.
I have one question again about the strength of this coupling D, or in general, the strength of the coupling between the cantilevers or whatever the elements are. How is it weak in some sense compared to I don't even know what, or is it strong? And again, compared to I don't know what? Can you comment on that?
It's a very good question, and I don't remember what we were using for this.
Because I put it to 0, I have uncoupled things, right? So uncoupled.
Right. So
then there must be a regime of weak coupling. And
the important thing to say is that once we have the coupling, we move to describe the system in its normal mode basis rather than at the original basis. So once we have them coupled,
I understand that, but I can still technically choose different numbers.
Yes, I agree. I just don't remember.
Probably defines your length scale for partial differential equations.
Right.
Is number 2.
No, partial differential equations are already, approximations. You start with a set of coupled ODEs.
Yeah.
And so the question is, when D is small,
yes,
I'm sure that there are solutions
yes.
which are not there when D is big, and what is small, big, and so that's my.
Okay, so if I look at 2 degrees of freedom, the strength of this D will basically select the difference in frequency between the 2 modes. Okay, the stronger the coupling, the more separated they will be. The weaker the coupling, the more close they will be in frequency. To get the plots that I was showing you earlier, with S1 and S2 and D1 and D2, I need them to be closer than the width of the response curves. So the interesting dynamics that I'm showing you is for relatively weak coupling.
But on the other side, I could first.
But did you understand what I was
Yeah,
trying to
yeah,
say?
but
I could solve the equations for strong D.
But I have my question is going in different directions. So let me put D to 0 and go into your bistability regime for one cantilever, 1 degree of freedom. And now I can put one of the two guys into the highly excited stable state and the other one in the weakly excited. Now I switch on a little D, and the question is whether the state survives.
Okay, so actually I have an example of doing exactly that.
And
But let me say a few things about the quantum, and even if
good.
people are patient, I will show you some other thing that we did there. Okay, so let me see if I can use this. Yes, it worked. So these are links to skip. So I want to say just a few words because I'm at -8 minutes now. A little bit about observing quantum dynamics of these nonlinear resonators. The thing is that today, and maybe I should have updated this slide some time ago, but mechanical systems are almost routinely, depending on the particular system and where it's being done, are almost routinely being cooled to their quantum ground state. Maybe the statement is too strong, but many labs in the world know how to take a resonator and cool at least one of its modes to the quantum ground state. That means that the energy of that state is 1/2 h bar omega. There are no additional phonons in the system. There's no excitation beyond that vacuum state of the resonator. But seeing actual quantum behavior is much harder than that. So by actual quantum behavior, that would require entangling two coupled resonators, one to the other. Now, there has been some work. I can give references later. But when we did this work, we tried to say, well, can we just, so we tried to pose the following question. Can I just look at the mechanical resonator, like this Duffing resonator that I started my talk with, and gradually cool the temperature, make the system colder and colder, increase the frequency, so make the system smaller and smaller. The smaller the resonator, the higher the frequency, to the point where when I compare the quantum energy scale, h bar omega, to the thermal energy scale, kBT, then kBT will be much smaller than h bar omega. At that point, I should be able to see the quantum discrete energy levels. I can see quantum mechanics, and when I look at the dynamics, the question is, will I be able to see something that's not classical? So as I look at a system, make it colder, make it smaller, make it its interaction with the environment as minimal as possible, will I be able at some point to say, now I saw something which cannot be explained using classical physics. Now I saw something in the dynamics which can only be observed in quantum mechanics. This is what we asked ourselves. So are there clear experimental signatures of this classical to quantum transition if I'm just looking at one mechanical degree of freedom?
I think that on top of the temperature, you need to make it have the coherent.
Yes. So I said I want to have the interaction with the environment as small and minimize that.
My point is that you need to have the interaction between two quantum things. You need to have interaction between two quantum two things in your system. You need nonlinear.
Okay, so you're jumping already to the first part of the answer to this question, and that is so this is the kind of calculation that we did some time ago. We basically said, let's take a particular oscillator and just numerically study its quantum dynamics and compare it to the classical dynamics. So all the parameters, exactly the same parameters. The only thing that's different is that on the left, I'm using quantum dynamics. On the right, I'm using classical dynamics. On the right, what we're seeing are very many, I think 10,000 points here that are the initial conditions that I'm choosing for the system, where this axis is the position, and this axis is the momentum or the velocity. And on the right, what I'm plotting is the best thing we can plot in quantum mechanics, or at least the best thing I like to plot in quantum mechanics, which is the so-called Wigner distribution. So the Wigner distribution is something that you can generate from the wave function, from the quantum mechanical wave function. It's almost like a probability distribution of classical states, just that the classical states are these blue dots here, and that the density of blue dots can also only be positive, whereas this distribution, here it's blue, it's positive because it's made to look like this distribution here, but when it's quantum mechanical, it can become negative, this Wigner distribution. I'm not going into the details, I'm just giving you the short version of the story. But if you take and integrate through at a particular position all the momentum, all the values of the momenta, whether classically or quantum mechanically, what you do get is the probability distribution of finding your system at the position X. So that's not a true distribution. It's not a true statistical distribution, but when you integrate it in one direction, it does give you the statistical distribution of the other variable, of the other canonical variable. So what I'm doing here is I'm showing you some Gaussian distribution here in phase space, both quantum mechanically and sampled by 10,000 points classically. And now I'm just going to turn on the dynamics. And what we're seeing is that the dynamics look quite identical. And that's because this is a linear, this is a harmonic oscillator. So the harmonic oscillator is basically classical. So the only real difference between the quantum and the classical is that I have a Heisenberg uncertainty with X and with P. But if we're experimentalists and not theorists, there's always uncertainty also in the measurement of the initial state. And so really it's quite similar. It's quite similar. So what we realize is that if we want to follow a single degree of freedom, it better be nonlinear. So here I'm showing you this Duffing equation of motion, again, the one that I started with. Sorry about the fonts here. If I consider H bar and compare it to the physical dimensions of the system, so D is the width of this mechanical elastic beam, and M is its mass, and omega is the frequency, this gives me a natural dimension to compare with H bar. And here I've chosen H bar to be only less than 0.5% of what I have here in the in particular mechanical system. Let me just jump to the simulation here. So what we see in the quantum mechanical simulation is that it really becomes red. So this distribution becomes negative, which means that we're seeing something quantum mechanical. The coherence here is not great. So what we're seeing is that we lost a lot of the initial information that we had here, but for the initial few oscillation periods, we had a very nice pattern of red, blue, where the classical pattern was simply white. So there was nothing there, but quantum mechanically, there was some sort of an oscillation between negative and positive values. And here I let it run a few hundred oscillation periods. And what we see classically is oscillations at these two solutions that we had to the system. If 0, 0 is somewhere over here, this was the small amplitude oscillation, and this was the large amplitude oscillation. And the fact that it's smeared here is because I have temperature, I have thermal noise here. And so the system is being constantly kicked around, but around these two steady state solutions that it has. If I look at the distribution, it has very high peaks here in the classical case, whereas here I clearly see something that's quite different from that. I mean, there's some information here with these two bumps here that there were two preferred states here of the system, but clearly this quantum mechanical system is already quite different from the classical one. Okay.
Sorry, can I ask a question? I'm kind of lost. What exactly are you simulating in quantum mechanics? Because you need some system with maybe Hamiltonian or what Lindbladian, which yields this equation of motion.
Exactly. So it's this Lindblad trick where we couple the system to a bath in turn, and simulate the fact that it has a temperature. I'm trying to hide all the details under the carpet, but I'll show the references here at the end. You can, and if not, send me an email and I'll send you the details. Yeah, but you're exactly right. But what I wanted to emphasize is that here I took KBT to be equal to h bar omega. So these two energy scales are, in this case, exactly the same. What I was looking for was the first steps away from classical behavior. So let's just increase the temperature slightly and make it 2h bar omega. Okay, so make it closer to the classical situation, and now follow the dynamics. Okay, so again, I'm starting with similar looking blobs. This is coming from the wave function. This is just sampling 10,000 points out of the same probability distribution as we have in the quantum case. And again, have that red-blue oscillation where classically I just had white. And I think I'm letting this evolve again for a few hundred oscillation periods of the resonator, sorry. And here you're already seeing that even throughout the dynamics, things look quite similar, but there is a deviation away from classical behavior. But here the two peaks are now much more pronounced than they were when I was more quantum mechanical. So now I'm really approaching the classical regime, 800 oscillation periods. Classically, I have these very well separated blobs here. So there's a region here of oscillation amplitude that I will never see if I measure my classical system. Here I have these two peaks, but in between I have a finite probability of catching my oscillator at that oscillation amplitude, okay? So what we're seeing here really is the first deviation away from what we expect to see classical. And this was the main message of this work that we did here, is that if you use a nonlinear mechanical resonator in its bistability regime, so in the regime where there are two possible oscillation amplitudes, if you can cool the system sufficiently such that classically the transitions going from one solution to the other, which can still happen if there's noise in the system can get kicked from one steady state to another steady state. But if it's very, very cold, then this is basically exponentially suppressed, but the quantum fluctuations can still kick me from one solution to the other. And going to your question of coherence, I really need this kick to occur at very early stages of my dynamics. So at some point I lose coherence, that's clearly obvious here. But if something that was supposed to end up here is kicked by some quantum fluctuation to the basin of attraction of the other state, then it'll end up not where it was supposed to end up. Okay, so this is something that I was hoping, this was 2000, I don't remember, 7, 8, 9, but we published this. I was hoping that someone will do this experiment. It was never done. So it's much more complicated than one thinks. And of course, the main obstacle is that you really need to be able to know the actual temperature of the system independently. You really need to know that you cooled the system, and you don't want to think that something is happening because of a quantum fluctuation, but in fact, it's coming from having more thermal noise than you thought you would have. It's a difficult experiment to perform. A more recent paper that we did is related to quantum limit cycles. I saw you have a poster out here for this meeting in Dresden in a few months that's going to talk about these quantum limit cycles and other questions related to that. But I think I'm out of time. But this is basically in the similar spirit of this paper, trying to see how you can take what are called limit cycles in classical nonlinear dynamics and express them quantum mechanically and study them. And seeing the transition from the behavior of classical limit cycles as you transition to quantum limits. So thank you for your patience.
Thank you. Okay, thank you, Ron. We have lots of questions, but still, there are more. Yes.
Can I ask, so when you were discussing this quasi-static switching, you remember this, you were showing this G versus K plot and then jumps from one term to another. So I was wondering, so you basically showed some kind of stability, like, so you had your partial differential equation of the field B, and then you determined the stability of this field B.
I determined the stability of particular solutions for the field B. Okay. And those were particularly simple solutions, because the solutions that I was looking at that I labeled B0, B1, B2 were oscillating at one eigenmode of the array if it were linear. If the array were linear with fixed boundary conditions, then you know that you have to fit in integer number of half sine waves, right? Okay. Between them. So these are the modes that end up being observed in this dynamical system. So I can take my differential equation and substitute for B one of these eigenmodes, okay, with particular wave number K, and I can linearize the equation and study the stability of that mode. It's actually simpler than you might expect.
So you consider one specific solution with one wave number, and from there you obtain this stabilities.
Yes. And it does have on the right here, if you remember, it did have this region where it was bistable. Yeah. It could either be zero or have some finite value. Like we had for the single degree of freedom case that I started my talk with. Okay. Now all of this is described fairly pedagogically in these two reviews down here. And then these are the actual papers that are some of the main papers that we published over the years. I think this what's it called? Physical review research. Physical review research, yeah. This is also quite pedagogical, I think. It goes into the details of how the calculations were done and so on. But these are really fairly written as reviews where you can actually use them to learn everything from without knowing much to begin with. So for many of the questions that you asked me, the answers are here.
I have a very nice question. When you are talking about the stability, what is the definition of stability that you're using? Is it like a Lyapunov stability, or
I'm not sure
what is the measure of stability that you are using to define?
It's just whether so I look at the dynamics after I linearize the equation of motion, and I know that the solution of the linear equation of motion will be e to the some I lambda t, but this lambda in general will be complex. And all I'm interested is whether the real part will decay, as e to the minus lambda 0t, or explode as e to the lambda plus lambda 0t. And if it decays, then this solution is stable. If it explodes, then the solution is unstable. Did I answer the question?
Thank you.
Simplest kind of thinking. way of thinking about it.
Any more questions?
And as someone asked me, since these are again complex numbers, then this is done in a complex plane.
Okay, looks like there are no more questions. Then let's thank Ron again. Thank you very much. And there should be some food outside. Enjoy. I don't know what kind of.
Noch wieder verletzt.